Hey, thanks everyone for coming out today. I really appreciate it, whether you're here in person or tuned in online. Today we have a load of topics to talk about, from MalDev to Syscalls to BOFs. Oh my. All right, so with that said, before we get on into it, just quick disclaimer. This is given on behalf of myself and not my employer. Now, let's have some fun. So a little bit about myself. As mentioned, I'm Scott Taylor, and I'm currently a red teamer at Sony. I've done previous red team work with T. Rowe Price and MITRE as well. Before I got into the red team space, I started my roots as a Linux sysadmin, first Linux operating system, Red Hat version 7. I do have a couple of certs and degrees. So with today's talk, we're gonna go over the whole story of the past decade of red teaming. Specifically more on the post-exploitation side of things. So we'll start out with a little bit of PowerShell, some C#, dig into some concepts like process injection, and then get into the really nitty-gritty stuff like syscalls and BOFs, where we're currently at. So as we're going through this talk, the thing that I like to think about is your typical red team operation. Oftentimes we'll start with a phishing engagement. Bleh, hard, challenging, it might take weeks, months to land that shell. But when you actually land, what do you do? Right? So if we were to go back in time a decade ago, we would probably start cracking out some PowerShell, right? That ugly blue background program. So, we obviously had to realize, well, we can't just keep dropping tools onto disk and AVs eating it all up. So we had to start living in memory. So PowerShell was the way we decided to go about that. If you look at this little screenshot, I realize it's a little hard to see, but basically on all these major operating systems, you have PowerShell installed. Easy win there. And we're living off the land, so we're not downloading additional tools to perform our post-exploitation. So yeah, we started coming up with all these weird syntax, right? Because PowerShell, right? And PowerShell IEX, and we started downloading tools, running it in memory. It was all fun and games, right? So if you're not familiar with this, you can think of it as like curl pipe to bash, if you're more of a Linux user like myself. So of course, because everyone started using PowerShell for post-exploitation, we started using a lot more PowerShell tooling, hence why every tool started with Power all of a sudden. So all these tools started to develop, and you could do all your post-exploitation using PowerShell, from reconnaissance to credential dumping, to exfiltration, all these steps you could do with PowerShell. So this was all fair and good until Microsoft, kind of stopped the PowerShell party by coming out with the anti-malware scripting interface. Boo. Right? So we started having to deal with AMZ. So every time PowerShell program started, all of a sudden, we found this little amz.dll library start poking in. So ultimately, what that allowed AV providers to do is take all your PowerShell content before running it in memory and saying, hey, is this legitimate? Do we want this to run? Right? And then, of course, if it had a bad signature, it would block it before running. For a more technical view on this, my apologies, I know it's a little blurry. You can blame Microsoft's documentation for that. Basically, not just PowerShell, but also VB-script for all those Office macros and various other applications. They all started getting pegged by AMZ. So ultimately, all of these tools that we're using to operate in memory were now getting caught. So obviously, we didn't go down without a fight, right? We had all these obfuscation tools like invoke obfuscation, of course. So we could try to scramble up what it looks like, try to keep it, obfuscated. We could download or downgrade our PowerShell versions to less secure versions, or of course, we could go after AMZ itself, right? There's all kinds of AMZ bypasses out there, whether you're blocking up the scan buffer and all that fun stuff. So that's, ultimately what happened with PowerShell. So obviously, as time went on, it got more and more challenging to use PowerShell. So we had to look for the next best thing. Now, PowerShell, we figured out, well, that's built off of this .NET framework thing by Microsoft, and it uses the common language runtime. So looking around, we started figuring out, well, there's this other thing called C#. Right? So that's ultimately where we all started pivoting to on the red team side of things. All right, so we said, well, let's rewrite all of our tooling. Let's all switch it to C# and use the .NET framework still. So the thing is with C#, right? You have your PowerShell, which is interpreted. You can just write your script, click play, you're good to go. C# on the other hand is a compiled language. So all your C# programs, you have to compile them, but it is technically still managed code. So you need this little thing called the Common Language Runtime. So when you go to run your exe, you can't just necessarily run it on any box. You have to have the Common Language Runtime available, which takes your C# program and handles it properly. So if you're familiar with Java, it's a similar deal with the JVM. All right, so with the Common Language Runtime, don't worry, you do not have to see the details of this picture. This is just for reference. But if you look at all these different Windows build versions, all of them have some form of the Common Language Runtime on them already. All right, so we're still living on the land, right? And we're able to use the .NET framework, right? Very, very powerful framework in Windows that allows us to do deep level things. But yeah, and like I said, we had to rewrite everything. So again, we can do all of our recon, our credential dumping, all these tools started coming out, being available on GitHub. So, it was kind of just a natural progression, making our way from PowerShell, and now we're on to C#. But of course, we can't just take all these compiled C# exes and drop them on disk. That's a big no-no. We already learned that lesson quite a few years ago. So a buddy of mine wrote this tool called Donut. How many of you guys are familiar with Donut? Anyone out there? Yeah, big fan, right? So awesome little program developed by the Wover. You can take your C# program, compile it to an exe, and then instead of using it as an exe, you convert it to shellcode, right? So if you're not familiar with what shellcode is, shellcode basically is very low level instructions that are handled by the processor. So it's really great for taking your program and injecting it, which we'll talk about in just a second. So along with the C# program in your shellcode, it also takes a copy of the Common Language Runtime, right? That little thing that you need in order to run C#, and that also is packed into the shellcode. So your C# program and your CLR all jam-packed into the shellcode, and it's position independent, right? So with that being said, there's no additional dependencies required. You can take your shellcode, inject it, and you don't need any external dependencies. Super, super, super cool. So then we have to talk about process injection. So in order to do that, we're going to leverage this thing called the Win32 API, right? And a couple of folks certainly talked about this earlier today with the kernel talks. The Win32 API is essentially all of these DLLs that Windows offers. So if you're not familiar with the DLLs, basically it's a dynamic link library. And I honestly like to think of them as similar to Python packages, right? You can install the map package and then use functions like add, subtract, divide, whatever. So in this case with DLLs, you can take your Windows DLLs or your libraries, import them, and start doing low-level Windows operations. All right, so creating threads, creating processes, all these low-level Windows operating system activities. So additionally, with the Win32 API, it's all publicly documented on Microsoft's website. So you can go and see, well, what can I do? What parameters do I need? There's no hiding behind the surface or anything like that. Very open. And just to make sure it's very clear, right? A lot of these DLLs are just sitting in the system32 directory, right? Not all these DLLs are part of the Win32 API, but for example, there's like the kernel32.dll, and that DLL is heavily used for low-level Windows functions. So, like I said, as far as examples go, you have the kernel32, you can create a process by using that. Another popular red team technique is dumping the memory space of LSAS. That function, there's a Win32 function that allows people to do that. In the debug help library, you can take a process that's running and dump its memory's contents. Guess what? That's what we like to do on the red team for LSAS credential dumping. So as far as process injection goes, Again, we can use the Win32 API, all those functions and libraries, in order to inject shellcode. So with shellcode injection, I like to think of it as a three-step process. First, we need to allocate space for our shellcode. Then we have to write our shellcode into that space that we just created. And then, of course, we have to run our shellcode. So the following functions can do that. And this is pretty much your vanilla shellcode injection process: virtual alloc, write process memory, and create remote read. So, with the donut, turning your C# tools into shellcode and then process injection, obviously we had to figure out a way to make this easy to use during our red team operations. And that's where Cobalt Strike came out with this idea of fork and run. So this quickly became the standard for how we used C# tooling in our red team operations. So essentially we would create a sacrificial process. So in my example here, right, you have your C2 implant running on a computer, and you spawn calc.exe. Very harmless, very common thing to do, right? And then you take your running calc.exe program and you inject shellcode into it. So this can be whatever tool you wrote, right? You can have, for example, Rubius, if you're familiar with that tool. Take any tool you want, inject it into calc, and start running your red team tools out of legitimate processes. So this is a great way to hide amongst all the programs. You can, obviously calc is a little weird. You can pick other more stealthy programs to inject into, but this quickly became the way to use C# tools. So over and over and over, we'd be creating processes, injecting into them, getting the output of our tools, and over and over and over, right? Just like this slide says, right? So just to clearly review, C# code, right? You write that up, compile it down to an exe, and then you convert that exe to shellcode using Donut. You take your shellcode, and then you create a process, inject into it, and then you profit over and over and over and over again. So this sounds like an awesome way to go about red team operations. However, of course, as all things go in the red team world, it did start to come to an end, right? EDR started getting better. We had to start dealing with API hooks, AMZ, and loads of other issues. So these are the two issues I'm going to focus on today with regards to Syscalls and BOFs. So getting into that, right? Let's talk about these Syscalls. So the reason we use Syscalls is because of this idea of API hooks, which, again, the kernel talks today did a great job covering API hooking. Essentially, to recap, we have EDR programs that go into any created process, and they started messing with those libraries that we were talking about earlier. So for example, if we take the kernel 32 library, there's that function that we use for process injection called write process memory. So basically what your EDR is going to do is you're going to say, you know what? I'm going to take that function and add a little jump instruction. And instead of just allowing anyone to write process memory wherever they want, I want to take a look at what you're writing in the process memory. So instead of just writing to memory, it goes off to the EDR. The EDR says, hold up a second, that looks like some malicious C# code that you're trying to run in that process. I'm going to block it. So this started happening all over the place. All these Win32 functions started getting hooked, is what we call it. And essentially, there's a lot more visibility as far as what functions we could use during our red team operations. So with this level of insight into our red team, or into the Win32 API functions, we had to go deeper. And this is when we start digging into the ntdll.dll. It's almost like it's trying to convince me that it's a DLL. But essentially, we have this library, which is the last library before you start hitting the kernel mode. So all of these ntdll functions are not documented, not part of the Win32 API. So of course, that means all the red teamers went in, reversed them, and tried to figure out how they work. So basically, with all these functions, this is essentially when you call Win32 functions, these all get funneled to the ntdll library. So you'll find that a lot of these functions start with NT, right, for the NT kernel. And basically, all of those functions started getting hooked as well, right? Even as smart as us red teamers are, the EDR companies are also pretty smart, and they started hooking all of the NTDLL functions. So then we started figuring out, well, okay, all these functions are getting hooked. We can't use them anymore. So what do we do now? So then we started going, of course, deeper. So in order to do that, researchers started digging into the NTDLL library and figuring out how that worked. So as mentioned, the NTDLL library is the last step before hitting kernel mode. So when we started digging into this, we realized, well, there's this idea called Syscalls, and by no means is this new. This is very well known. However, we started figuring out, well, this is how the NTDLL actually functions. And essentially, all of these functions have these syscall service numbers. So for any Linux users out there, you'll find that it's very similar to this idea of a Linux syscall, where you have an associated number with it. And you can do syscall number, and then it runs some kind of function to the kernel. So we started figuring, well, okay, this can work, right? You can't necessarily hook a syscall number. That's just not how that works. And we can avoid all of these hooks in these libraries or these DLLs that we're trying to leverage. So, people started doing exactly that. We figured out what the syscall IDs were. We started putting them in our tools. I think Dumpert was one of the first tools I noticed that started using these direct syscalls by calling the syscall IDs or the system service numbers. However, we quickly found out, hold up a second, those syscall numbers change from build to build, right? So we can't necessarily just hard code these syscall IDs inside of our tooling. So, I put in some examples here, right? That allocate virtual memory in the NTDLL. That one happens to have the same syscall ID across all these builds, right? That's awesome. However, if we want to create a thread using the NTDLL, those syscall IDs change from build to build. So of course, we can't rely on every single organization having fully patched up-to-date systems and having all the IDs be the same. So obviously we had to figure out how are we going to use syscall IDs, even though we have to, we don't necessarily know exactly what the IDs are going to be. So that is the ongoing challenge right now with leveraging syscalls during your red team operation. Basically, we have to figure out ways to find the syscall IDs without getting caught trying to find the syscall IDs. So obviously, EDRs don't necessarily like us poking around the NTDLL library. However, we can find these syscalls directly in that DLL itself. So obviously, a lot of research has been published about how to go about these methods. There's numerous ones out there, but at the end of the day, most of them revolve around digging into the loaded NTDLL in the current process. This can get a little dicey because EDRs, again, are putting in all those jump instructions and hooking functions. So it's not necessarily easy to know exactly where the syscall IDs are located. Or there's other methods out there where you take the NTDLL file on, in the system32 directory, you read it, and then start trying to dive through it and figure out what the syscall IDs are. So all these methods are out there. And of course, it's kind of a cat and mouse game right now between trying to figure out how can I read my syscall IDs or resolve them versus, how do I do that without getting detected? So if you do want to, learn more about some of these methods that are out there, there's an awesome blog post by MDSec. They have, a really good verbose write-up on how you can find all of these syscall IDs with different variations. So, that's kind of the cat and mouse game, but ultimately direct syscalls are the way to go as far as process injection is concerned. However, we still have to deal with that .NET framework. And that's where we start talking about BOFs. So we talked about this earlier with PowerShell, and PowerShell has to deal with AMZ, right? That's reading all the content to your PowerShell script, figuring out if it's bad or not. Unfortunately, it's made its return to C#. So if you start using the .NET 4.0 or greater common language runtime, that common language runtime, or the CLR, that CLR has AMSI built right into it. So anytime you run your C# tool through your CLR, you have AMSI looking through all the contents of your C# code and figuring out, well, is it good or bad? So with that said, there's more and more tools out there getting better at detecting C# memory or C# tooling in memory. So of course, history repeats itself. We've got ways to obfuscate it. We're again going after AMSI. We're trying to downgrade which C# version we're using or what CLR we're using specifically, right? So, very much same exact deal as PowerShell, but now we're here with C#. So, of course, we have to switch up the tooling again. And that's where BOFs come in. So BOF is a feature specifically developed by Cobalt Strike. And basically, it allows you to run code without the need for the .NET CLR. Additionally, there's no fork and run required. So that's pretty sweet. We're not creating processes, injecting into them 24/7. All the activity is in process. So we have our implant running out of the box, and you're running your malicious code inside of that process. And then again, because this is specifically for Cobalt Strike, there is a reliance on the internal Cobalt Strike Beacon API, which makes it a little hard to use for custom tooling, but we'll talk about that in a bit. So this all sounds great, but what is it actually under the hood? So your Beacon object file is honestly pretty straightforward. It's a really small compiled C program, specifically in the format of a COF file, or the common object file format. Traditionally, if you see this, see a compiled COF file, it'll have like a .o ending for an object file. So again, these are really small programs. They're under 3 kilobytes. So it makes it really easy, lightweight, portable to use inside of your current process. It's not this behemoth of a tool that you have to inject. And another sweet thing is position independent code. So you don't have to worry about external dependencies, similar to the whole donut deal, right? It's all self-compact, very easy to use. So when I started digging into these BOFs, trying to figure out, well, what actually is this, right? TrustedSec put out an awesome repo of situational awareness BOFs that you might use during your typical engagement. So a lot of common things that you need to do on a red team operation have been rewritten to BOFs. Very simple things, such as LSing, right? You got to figure out where the files are, or if you want to look at environment variables. Common things that you might do during your red team operations. However, as time goes on, there's more BOFs added to this repo, such as all the ADCS hype, if you're familiar with that. There's been quite a bit of research now in Active Directory certificate services. And there are BOFs now available to use during your red team op if you want to use BOFs to attack them. So very cool resource. Super happy that this is out in the open. All the source code's out there. Again, small C programs that you can use and that don't rely on the .NET framework. So now, what I personally like to do is write my own tooling. So why would I like to do that? Well, unfortunately, Cobalt Strike is a victim of their own success. Without heavily modifying or customizing Cobalt Strike, it does get signatured pretty easily. I'm not trying to shame Cobalt Strike. It's an amazing product, but threat actors in the wild are using cracked, not allowed versions of it. Therefore, EDRs like to signature it. So personally, when I'm doing my red team operations, I like to use my own tools, ultimately because it has a higher chance of evading signatures. You can understand exactly how your implant works, right? If it breaks, you want to know how to fix it. And also, you can customize it to do whatever you like. So there we go. So personally, I am a big fanboy of Mythic C2. Is there any Mythic C2 fans out there? Anyone? Yeah, my boy's back there. There you go. Mythic C2 is fantastic, written by It's a Feature or Cody Thomas over at Spectre Ops. And ultimately, this C2 is great for writing your own custom agents. The framework itself is really solid, and there's tons of agents out there. Of course, the two people with their hands raised have written their own agents out there. Shout out. So there's all kinds of tools out there, right? There's agents for C#, Golang, Swift, Rust, PowerShell, Python. tons of source material out there. So if you're hesitant, you're like, well, I only know one language. There's probably, an agent out there if you want to dig in yourself. You can start learning about how Mythic agents work. Personally, if you ask my team that I currently work on, they're going to say I'm a big Golang fanboy. So of course, I picked up the Poseidon agent, which is written in Golang. So first thing I wanted to do was figure out, well, how do I do this whole fancy syscall thing in Go? So as I started searching around, I found this awesome Golang package called Banana Phone. Fantastic name. And basically, this does everything that I need to do. Again, Sisto, the researcher who put this together, awesome, awesome work. Basically, it'll do two things for you. It'll find those syscall IDs for you, and it'll allow you to make syscall requests. So in this case, I realized the code might be a little hard to read, but I just tried to put a little red box around it. Basically, there's a function built into Banana Phone where you can say, get sysID, and then specify the name of the function you want to use. So in this case, awesome, I want to allocate memory for my shellcode. In that case, I also want to use the NT allocate virtual memory function call from NTDLL library. So in this case, Banana Phone says, no problem, here's the syscall ID. And then I want to go use it. And of course, Banana Phone has an awesome function called syscall, and you can make your syscall request. So in this case, my variable here is just the ID of my syscall, and I pass in all of my needed parameters for that function. So very easy to get started with this kind of tooling. There's tons of libraries out there for languages. This is specifically what I use in order to get syscalls to work in my implant. So now, obviously, the next thing I want to do, I can do my process injection, be highly evasive, avoid all those API hooks, but I want to start using BOFs. And this is where really the big challenge comes in. There's a cool project developed by the folks over at Falcon Force called BOF to Shellcode. And of course, this sounds exactly like what the name implies. It's very nice. I can upload or provide a BOF file, right? That little compiled C program. Take that and give it to the BOF to Shellcode Python script. And with that little script, it will turn it into position-independent shellcode for me to use, right? Very, very easy to use. So I can take that shellcode, of course, pass it to my implant, and start injecting shellcode. So now I have avoided the API hooks using syscalls, and I've avoided the .NET framework for AMZ. So now I can pretty much repeat my process of uploading BOFs and injecting them safely without needing the .NET framework. So the problem is this tool itself, the BOF to shellcode, doesn't take command line parameters. So for example, if you want to do ls and specify a directory, it can't do that. So this is where the whole challenge is with using COF files into your custom tooling. Fortunately, again, trusted sec for the win, they put out this tool called COF Loader. And this allows you to provide your command line arguments for the BOFs that you would like to use. So, and of course, as it mentions on the GitHub repository, you can run unmodified BOFs so it can be used for testing without a Cobalt Strike agent running it, which is exactly what I want. So tons of C2 frameworks out there have used this already. Sliver, Ratel, Meterpreter, lots of these popular C2 frameworks out there have used the COF Loader in it. So very cool, and shout out to Sliver, another Golang C2. So you can use this, specify your command parameters, and use this in your custom tooling. So here we go, next. Yeah, so in conclusion here, right, we are in the process of transitioning from the common language runtime, right? It's similar to the whole PowerShell deal. We got to be careful with the CLR getting picked up by AMZ, dealing with obfuscating tools and all that. Instead, we found our solution to move on from the .NET framework. Also, instead of using these generic Win32 API functions, we now can use direct syscalls, right? So now we can inject Use process injection in a more evasive way, try to avoid API hooks. And the last thing I want to touch on here is ultimately we have to be careful of our behaviors, all that OPSEC stuff we keep talking about. Basically, in my example, I talked about opening calc.exe and injecting shellkit into that. But honestly, if you inject a tool into calc that reaches out to the internet, that looks super suspicious. So be careful of what you do. Don't inject tools into proper processes that blends in. And last thing I really want to emphasize is don't be scared to dive in. A year ago, I didn't know what any of this was, but there's so much resources out there. You can very easily dive in, read blog posts, learn about it, and start using it in red team development or red team operations of your own. So with that, thank you very much for your time. If you have any questions, feel free to reach out on Discord or hit me up on Twitter afterwards. Again, thank you very much.